Good evening and welcome to Monday Night Calculus. My name is Curtis Brown and I am hosting. Oh no, yikes. My name is Curtis Brown. I got that really loud there for a second. I apologize for the feedback. That was me streaming on this video tonight. I have to claim though that I am not a full 100% mentally this evening. I have been come down with COVID, so I'm quarantined in my room here at home here in Saxey, Texas. So my apologies if that was a little bit of a rough start. Anyway, we are really excited here tonight to have Steve Kokoska and Tom Dick with us once again. I've also seen several students who have already made comments in the chat tonight, as well as many teachers. Very excited to see great attendance tonight, which is awesome. But without further ado, I will turn things over to Steve and Tom. Steve, I know we've already gotten one question via email about a different question. So I'll let you get started sharing your screen and talk about that. I also want to just call out really quickly that I saw that I had not posted the problems in YouTube earlier this week. My apologies for that. So teachers, if you went out there looking for the questions for tonight, I didn't have them out there, and that's totally my miss. So they are up there now. If you go and download them, you can use them later this week. And the solutions for January 23rd are also up there in that YouTube description as well. So hopefully all of the things are good to go now. And I'll turn it over to Steve. Away we go.
Thank you very much, Curtis. So tonight we're going to do integration using substitution in a minute. But we were lucky enough to get a
substitution in a minute.
Whoop, I still hear that feedback, Curtis. Did you fix that? That sounds better. So we're going to do integration by substitution in just a minute, but we were fortunate to get a question from, I think, a teacher this evening. And we really like those. Students, if you're listening tonight, please feel free to send us questions. We enjoy that quite a bit. This one had to do with the free response question and a particular way that a student might present the answer. So I believe, if I understood the question correctly, the question is, well, what happens if a student did all this down here in part D? And right where this says cosine, instead of cosine, they had written the function f like that, f of 1 plus 2k over n raised to the 1/2 power. And the question was, well, would that be okay? Well, let's sneak back up here. Oops, I'm sorry, to the very beginning of this question, where this function is actually declared in the statement of the problem. So where that function is named, a student can use that name throughout the problem without any loss of credit at all. And in fact, Tom, correct me if I'm wrong, but if a student in working a problem finds that it is convenient or easier to actually name a function, often we do that in volume problems. If they want to create their own name and use that in a presentation, that's okay too. So in my opinion, I believe if the student had written f of that expression, raised to the 1/2 power times 2 over n, they would have received full credit. Tom, agreed on that one?
Well, with just one slight amendment,
Okay.
Steve. If they wrote f in place of the cosine,
Yes.
they wouldn't need the 1/2 in there. Because
Yes.
that was in part of the function f.
Yes. Okay. Gotcha.
So it would just be f of 1 plus 2k over n.
Oh, I see what you mean. So you
Yeah.
wouldn't put this in here. Right.
Right.
Right. Gotcha. Yep.
Yeah.
Yep. So f of 1 plus 2k over n times 2 over n would receive full credit. I agree with you. Yep. I agree. Beautiful. Okay, Curtis, I'm going to shift a little and I'll go to our problems for tonight. I hope you did all of these. I thought I heard you mention something about the challenge problem for tonight, Curtis. Were you giving away Super Bowl tickets? Did I hear you say that? Or maybe not. Maybe that just was something that I wanted to hear. Anyway, we're going to look at integration by substitution. And the general idea here is to take an integral that looks very difficult in what I would call the X world. And we want to transform that. We want to write it differently. We want to bring it over into the U world where we can solve the problem, where it looks much easier, where we can do it. Now, I really enjoy this subject, and I do these a little bit differently than some other people, but I think I do this in a very logical way and in a way that I won't lose any constants or pieces to the problem. Now, I know that many of the students out there, many of your teachers out there have some really great students, and they can often look at a lot of these problems, just say, oh, I can do that one by just multiplying by 1 in a convenient form and putting the 1/4 here and the 4 here, for example, and that's fine, I get that. But we're going to talk a little bit more general tonight on how to do these, and so we don't want to lose any constants, we don't want to lose any functions, we don't lose any x's anywhere. So this is how I would do it. So this is a nice candidate for integration by substitution. Why? Because, well, I can look at that and I can see an outermost function, cosine raised to the 5th power. I'm looking for the inner function there, cosine, and I see its derivative, loosely speaking, hanging around inside, but really as part of the product in that integram. So a really good candidate, sometimes I make mistakes here, but a good candidate here is u is equal to the cosine of x. So what I do, what I'm thinking of now, is I'm building this bridge into the u world. So I start out by letting u be equal to cosine of x. That's going to be my transformation. I take the derivative of both sides in my way of thinking. I take the derivative with respect to u on the left, with respect to x on the right. The derivative of u is 1. What you take the derivative with respect to, there's the du. Derivative of cosine minus the sine of x dx. And I always do one more step here. What I do is I always solve for dx. So I think of those symbols, dx and du, as differentials, as variables that I can multiply and divide by. And so I always solve for dx. Why? Well, because dx is in this original integrand, and I've got to somehow work to get that into the u world. Okay, here we go. So here's the original integrand, and now I'm going to work to get that into the u world. This expression right here is sort of my bridge to go from the x world into the u world. Some of my colleagues don't like this because that expression has both u's and x's in it. But for me, that's fine. It's a fine mathematical expression. It is this bridge to get from one world to the other. So u is equal to the cosine, so there's u to the 5th. What about the sine of x? Well, I don't really have an expression for that up here, so I leave it alone. I substitute in for dx, that's du divided by the sine of x, and now I'm going to do some simplification. So the signs will cancel, that's a really good thing. The minus sign comes out in front, and this is really good because now I'm left with an integral in the u world, all u's, and I'm left with an integral that's very easy to do. So I just sort of use this inverse power rule, u to the 6th divided by 6, so there's the minus sign, plus c. Now I'm not done. This expression or this problem started out in the x world, so I've got to get back into the x world from the u world here. So I've got to kind of walk back across that bridge. So what's u equal to? The cosine. I substitute in, and there's my final answer. There's always some discussion, and I often get a question about this. Is it okay to use that same symbol c there? And yes, it is. We understand that the one symbol c could be different in the u world than it is in the x world, but that's okay. We understand as mathematicians it stands for an arbitrary constant in the appropriate world. I won't go through all of these in that gory detail, but that gives you a lot of ideas about how I do this sort of a problem. And you'll see this sort of method here as we progress through some of these problems. So how about this one? The integral of a plus bx squared divided by the square root of that stuff. This is a kind of a typical, I think, AP calculus exam question on the multiple choice portion of the exam. So A and B are constants. I didn't add that in the problems, but A and B are constants here. And what's a good candidate for U? Well, I think I might try what's underneath this radical symbol and why, because I have some good, and you have better calculus vision than I do, but I'm looking ahead and I'm thinking, well, if I take the derivative of that, yeah, I think I can see that A plus BX squared, and I hope the threes will work out. So here we go. So U is equal to 3AX plus BX cubed. I take the derivative of both sides. There's my du, and as usual, I solve for dx. And when I did that, notice that I factored out the 3 in that denominator. I got this far, and I could see a little bit better what was coming here. So, all right, we start in the x world. There's the square root of u in the denominator. I leave that expression with x alone, a plus bx squared. There's my dx, my expression for dx. And again, I'm lucky, some good things happen. The a plus bx squareds cancel, the 3 comes outside, or the 1/3, and that's an easy integration. That's u to the minus 1/2 plus 1, or u to the 1/2 divided by 1/2, so times 2. So there's the 2/3 u to the 1/2, and I bring everything back into the x world. That's a nice problem also. I wanted to remind you of one little thing here. Remember, you can always, well, 2 little things. Remember that you can always check these problems by taking the derivative here and see if you get the original integrand. And let's see, there was one other thing I wanted to remind you of. What the heck was it? Well, I'll think of it here as we move on. There was one other little thing. Let's take a look at part C. Here we go. So this is a good one. Arctangent of x squared divided by x squared plus 1. Remember, I'm looking for some sort of transformation, some expression of x that I can set equal to u so that I have its derivative as part of the product in that integram. And a good candidate here is u is equal to the arctan of x. Why? Because the derivative of that is 1 divided by x squared plus 1, and I can see that. I can see that as part of the integram. I'm still going to do the usual here. dx is, I'm going to solve for dx, and there it is, x squared plus 1 times du. And again, I know that many of you are really good at this and can just look at this sort of a problem and say, oh, I can see the u and the du. I can do it right off the bat. That's terrific. That's wonderful. I would suggest that you don't want to make a mistake here under the pressure of the exam, and write out a couple of steps here. So I bring everything into the u world. There's the u squared in the numerator. I'm going to leave that x squared plus 1 alone. Here's my dx. These cancel. Again, I'm left with a very easy integrand over there in the u world. 1/3 u cubed plus c, and I bring it back into the x world, and there we go. All right, well, now things get a little bit more difficult. Let's try part D here. I think you really need some good calculus vision in order to solve this one. What do you do here? X cubed times the square root of x squared plus 1. Well, what should u be? I think my natural sort of knee-jerk reaction is to let u be equal to what's inside here underneath that radical symbol. But the derivative of that is just 2x, and I've got much more than that hanging around inside that integram. So I'm thinking about this a little bit more. And I'm thinking, well, maybe what we might have to do here is to split this x cubed up into x squared times x. And when I thought about that, I said, well, okay, I can take this expression and solve for x squared. And that would allow me to bring x squared very easily into the u world. So I'm still going to let this be my original transformation, my guess at this anyway. There's my du, which is 2x dx, and I'm going to solve for dx as usual. And let's see what happens here. This is a neat problem. So I'm going to split this up into x squared times x. How did I know that? Well, maybe from doing lots of these problems, but also a little bit of good calculus vision here. I can see that this x is the derivative of what's inside there. Well, okay, plus or minus a constant. And I know that I can solve for x squared and get that into the u world. So that seems like a pretty reasonable step. So in this instance, x squared is u minus 1. I'll leave the x alone. I've got a square root of u. And there's my dx. Some good things happen. All the x's are gone. I'll bring the 1/2 outside, and I'm left with an expression entirely in u. Now, what happens? What happens if we make some sort of transformation, some sort of guess here at substitution, and we cross over this bridge and we try to get into the u world, and we're still left with a bunch of x's or an x in some way? Well, a couple of things. First of all, you may have made a bad substitution, or at least one that doesn't work. Or another possibility is we may be able to pull a trick. I don't want to use that word trick, but we may be able to use this mathematical idea where we can solve for x or x squared or some expression of x entirely in u. Okay, I've got an expression in u. I can integrate both of those pretty easily. Did I do that right? 2/5 u to the 5/2 minus 2/3 u to the 3/2. There's my plus c on the end. And I bring everything back into the x world, and I think I did a little bit of canceling. Did I do that right? Yeah, the 2's and the 2's cancel there too. That 1/2 goes all the way through. And there's my expression in the x world. Pretty cool. Pretty cool. Any questions out there, Curtis, if you're still with us?
I'm still with you. I don't think anybody's asked any questions in the chat yet tonight.
Okay.
But if you have some,
Oh, we've got
fire
some
away. I
coming
know
up
we've
here.
got quite a few students on tonight. So
All right, we've got a couple coming up here.
that'll be good. Well, you're not
All
going
right.
to ask me any tonight.
I won't. I won't.
I'm going to turn
right,
every
so let's-
question you ask into one for the audience. That's all I can say.
Okay. All right, so let's switch just a little bit. Let's still do some integration by substitution, but now let's take a look at definite integrals. It's still the same idea. We want to see if we can find a good transformation so that we can bring everything from the x world into the u world. But this time we want to make sure that we drag along the bounds. Now, there are two schools of thought here, I guess, a couple schools of thought. I mean, one thing we could do is we could neglect or not look at those bounds and just work with the indefinite integral and bring everything back into the x world and then plug in the bounds, and that's fine. But I think a more efficient way to do this is to bring everything into the u world, and that means drag along the bounds also. I think that's the most precise, logical way to do this. And I'll show you how I will do this one, and I think Tom will have a little bit of technology here. So this is a neat one. E to the 1 over x divided by x squared. What should u be equal to? Well, I see an inner function there of 1 over x. And I see its derivative, minus 1 over x squared, well, 1 over x squared, plus or minus a constant, as part of the product integrand, or integrand product. So I'm going to let u be equal to 1. Whoops, I'm sorry about that, Curtis. I don't know what happened there. So I'm going to let u be equal to 1 over x. There's du. Whoops, there we go. I'm going to solve for dx. And now, remember, since this is a definite integral, I need to drag along my bounds. So when x is equal to 1, I'm simply going to plug it in here. I get a 1 over 1. When x is equal to 2, the upper bound, I get a u equal to 1/2. Okay, so let's arrow down a little bit here and take a look at this first step for a minute. Here's my bridge going from the x world into the u world. I'm going to change my bounds first. So when x was 1, u was 1. When x was 2, u was 1/2. And notice something that's happened here. And that is that the lower bound is now the larger number. And that's okay. That might happen. I still follow through, do everything in the logical way here. That's fine. You know that we have a property of definite integrals, which allows us to flip those bounds and put a minus sign out there, and that's okay. And I may do that in another problem, but you don't have to. So, okay, I've got e to the u. I'm going to leave the x squared alone. There's my expression for dx. And the x squared's canceled. The minus sign comes out in front. And I think there might be a missing d in there. It's very, very small, Curtis. It's really hard to see. So now I'm going to integrate e to the
I
u.
see it, Steve. You had
Do
to
you? Oh,
zoom
good.
in for
Thank
me,
you.
though.
Thank you. That's one of our easiest integrals, e to the u. That just becomes e to the u. And now I'm going to plug in these bounds, e to the 1/2 minus e to the 1. There's still a minus sign out in front. And I think what I did to simplify this just a little bit was to carry through that minus sign. So I've got an e minus the square root of e for a final answer. It's kind of a neat problem. Tom, a little bit of technology. What do you think?
Sure. It's
Okay.
looks like a good place for it. All right.
Fantastic. All right, there you go.
Okay.
All yours.
All right. I'll try to share my screen here. Let's see. Well, I'm clicking on share screen, but nothing is happening.
I think I gave up
Yeah,
your screen, didn't I? Yes, I think I did.
yeah, I think you did.
Try it now, Tom. Let's see what happens.
Okay. Oh, interesting. Well, my apologies. I'm not sure.
Maybe we won't do technology.
Yeah, I'm clicking on share screen, but I'm just not getting anything.
Is there a window behind your window there? Maybe it's not coming to the front.
Oh, wait, here we go. I think we might be all right now. So let me give this a shot, and thanks for your patience.
Oh, sure. Hey,
How's that look?
fantastic, Tom.
Okay. Great. So just wanted to, illustrate the kind of check you can do on your definite integrals and indefinite for that matter. I'll make a little comment about that. By using the numerical integration capabilities, you don't need to have a computer algebra system to do a nice check here. So what I'm going to do is just pull up the math menu and hit number 9 for the integral. And I'm going to put in the original integral that Steve had. It was the integral from 1. Oops, let's see. Go down here, 1 to 2.
Yep.
And we had, I believe, E. Oops. All right. Try that again. Yeah, there we go. E to the 1 over x.
Yep.
And then that was divided by x squared. Okay, and then we get a value there. Now, in doing that substitution, when one ended up with the u integral,
Yep.
If you forgot to get your limits of integration into the u world also, a really common mistake a student might make would be to leave those limits of integration as they were. So let's see what would happen if I use the same limits of integration, 1 to 2. And I think in the u world, we had just the e to the x, right?
And there was also a minus sign.
There's also a minus sign. That is correct. So let me back up here a little bit. And let's insert a minus sign in there. Excellent. Right. Now we'll go. And I will actually put in the u. and we'll be integrating with respect to u.
Cool.
And that's by far, I think, in that making that move on substitution, that's the step that a lot of students will forget, is to put their limits into the u world. And so when we enter this, oh, it's clearly not right. Okay, something's clearly amiss here. But if we had used the, I think what I'll do is take advantage of just copying this down and editing the limits of integration. Let's see, what we should have had was, I think there was a 1/2 on top.
Yep, that's correct.
Notice I'll just leave the limits in the, let's see, I think it was from 1 to 1/2.
Yep.
And I'm leaving the negative there. You went ahead and switched both of those, but I'll just leave it like this. And let's enter again. And there we see the nice match of the values there. So that's a really nice way to check things. I would also point out, if you're just doing a purely antiderivative, like the number 1 problems that Steve was looking at, what you could do is just arbitrarily turn those into definite integral problems to check out your answer. What you can do is pick 2 limits, do the numerical integral of the original, and then take what you think is the antiderivative and plug in those 2 numbers and take the difference and see if it matches. Basically applying the fundamental theorem. So lots of nice ways to check these things. Okay, I will stop sharing and give it back to you.
Okay. All right. Here we go. Let me see if I can make that full screen again. Hey, how about that? All right, well, let me do a couple more that are definite integrals, and then we'll take a look at some sort of different problems here involving maybe substitution. So this one is 0 to pi over 2 sine x cosine of the cosine of x. And Tom, you reminded me of something here about some common errors. I think one common error we often see here is with this sort of expression. Whoops, I'm sorry about that. Some students think of that as the cosine of x times the cosine of x. They read into that and see another x in there, and that's not true. This cosine of x right here is actually the argument on this cosine. So, all right, how the heck am I going to do that one? I got to search for an inner function so that I have its derivative as part of the integrand product. And indeed, that circled cosine of x, I know the derivative of that is minus the sine, and I've got that plus or minus a constant. So let's follow through with this one and see what happens here. I'm going to let u be equal to the cosine of x. I'm going to let, therefore, find, du is equal to minus sine x dx. Terrific. And I'm still going to follow through here, solve for dx. That would be minus du divided by the sine of x. This is a definite integral. So I want to drag along the bounds. When x is equal to 0, I need the cosine of 0, which would be 1. When x is equal to pi over 2, I need the cosine of pi over 2, and that's 0. Okay, here we go. Let's take all of this information here, and let's use that to build this bridge and bring everything into the u world. Here we go. Here's the original expression. I'm going to leave the sine of x alone. Because of my substitution, now I have the cosine of u. Dx is minus du divided by the sine of x, and some good things happen. The sine x is canceled. There's a minus sign out in front. And this time, I think, to make things a little bit easier for me, I'm going to invoke that property of definite integrals. So I am going to switch the bounds, and that means I need to multiply by a -1. So this would be negative times a negative. So now I have a positive out in front here. And that's a pretty easy integration, what I might call integration by inspection. So the integral of the cosine is just the sine. I've got the sine of 1 minus the sine of 0. The sine of 0 is 0, and that just becomes the sine of 1. The sine of 1 radian. So that's the exact symbolic answer, and that's pretty cool. I think that's a good candidate, too, for a multiple choice question. All right, I hope some of you had the opportunity to try some of these problems. This is a good one here, I think, in part C. Let's take a look at 1 divided by 1 plus the square root of x raised to the 4th power. When you look at this one, like me, you might be at a loss here. How am I going to solve that one? What should u be equal to there? I mean, my first impression or my first idea was, well, maybe I need to be painful, but maybe I need to expand out that denominator. I'm a little leery about letting u be equal to 1 plus the square root of x because I don't see the derivative of that anywhere as part of that product integrand. But let's see what happens here. And remember, if you make a mistake, that's okay. You just go back and you try a different sort of substitution. So let's let u be equal to 1 plus the square root of x. Derivative of both sides, 1/2 x to the minus 1/2, derivative of 1 is 0. Solve for dx. There it is. And now my calculus vision here is helping a little bit, I think. I can see here by this original substitution, I can actually write an expression for the square root of x, in terms of u. That would just be u minus 1. Why did I do that? Well, thinking ahead, when I substitute in for dx, I don't have anything that's going to cancel with this. So looking ahead, I got to get some way to get rid of that x, to transform it into u's. And so that's why I made this extra step. I got to drag along the bounds. When x is 0, u is 1 plus the square root of 0, 1. When x is 1, u is 1 plus the square root of 1, 2. Here we go. Let's see what happens here. Hope this works. Here's the original expression, 1 divided by u to the 4th. This entire expression right here is dx. And I've got everything in the u world right away. I'm going to bring the 2 out in front. And what I'm going to do here is to write this as 2 separate expressions. In some sense, I'm going to multiply through that 1 over u to the 4th through this expression. I've got a u to the minus 3 minus u to the minus 4. Holy Toledo, a lot of minus signs floating around there, but easy antiderivatives. U to the minus 2 over minus 2, u to the minus 3 over minus 3. So this becomes a minus sign out in front, plus sign here. Remember, these are now bounds in the u world. There is no need to go back into the x world. And in my opinion, that introduces more chance of an error anyway. I'm going to plug in the bounds. Let's see, did I do this right? Minus 1 over 2 squared 4. Yeah, minus 1/8 plus 1 over 24. There's the minus now. I'm going to subtract off what I get when I plug in the lower bound. Minus 1/2 plus 1/3. I found it easy to put everything in terms of a denominator with 24. And I think when I simplified everything, I got a 1/6. Curtis, I hope you got that answer and working these problems out. I'm not going to check your homework tonight, but I hope
I appreciate that. I appreciate your faith in me, Steve.
I hope you got that one. Okay, good. Here's a nice
I checked
one.
the solutions thoroughly.
Oh, good. Okay. Here's a nice one indeed. This is actually, I'm going to add a little bit off to the side. We don't do this probably often enough. I apologize for that, Curtis, but this is a BC problem. It still involves integration by substitution. So this is e to the square root of x, and it is a definite integral. And this is another one of those problems. Well, it seems like the natural solution to this would involve u equal to the square root of x. It seems very reasonable, but I don't see its derivative anywhere as part of that integrand. So I'm going to use sort of the same strategy that I did a moment ago in that previous problem. So here we go. U is equal to the square root of x. Take the derivative of both sides. Remember, this is really just x to the 1/2. So 1/2 x to the minus 1/2. I'm going to solve for dx. And thinking ahead, using my calculus vision here, I don't have any extra square roots of x in there at all, but I do know that this expression right here is u. So there's a nice way to write dx entirely in terms of u. Definite integral, I've got to drag along the bounds. When x is 0, whoops, I apologize for this. I apologize for that bouncing there. U is equal to the square root of 0, 0. U is, when x is 1, u is equal to the square root of 1, just 1. Here we go. Hey, this is a case, oddly, where the bounds remain the same. So 0 to 1, e to the square root of x dx becomes 0 to 1, e to the u, there's dx. And now what do we do? Well, this is a BC problem, and here's what I'm going to do. Remember that this variable inside here is just a dummy variable. So I could use any letter in place of that u. I could use T or S or W if I want. But to make things a little bit easier, I'm going to write it in terms of X again. Now, this isn't that I've gone back into the X world. It's just that I have changed dummy variables to make the next step a little bit easier. Because how do you integrate this? How do you integrate that expression? Well, that's an integration by parts. That's a classic integration by parts where I have a polynomial times a transcendental function, e to the x. So classic problem. Now, a little bit of an aside here, Curtis. In these sorts of problems where we have a definite integral and we use integration by parts, many students do in fact go off to the side and they work with the integral of x, e to the x dx, and they work this all out and they find their antiderivative, and then they go back and worry about the constant out in front here and the bounds, and that's fine. The way that I learned this, the way that I generally do this, if it isn't too complicated, is that I'm going to drag along the bounds with me as I do this. So let's see if I've got this right. I let u be equal to x, and dv is going to be e to the x dx. So let's see, I've got to find du, that's just dx, that's easy. V is equal to the integral of e to the x, that's just e to the x, that's easy. Let's put this all together with integration by parts. So let's see, there's the original expression. Here's my 2 out in front. This is going to be u times v. So x e to the x minus the integral of v du. So v du, yep. And there are my bounds. The way that I like to do this is I'm going to put all of this within brackets and write the 0 to 1. There are various ways to denote this. Some people do the integrand, this integral, we'll put the 0 to 1 here, and we'll put this expression in brackets, and that's fine. I tend to put everything in brackets, and I'm going to evaluate everything when I'm all done here, when I've got my final antiderivative. So I've got an x e to the x, the integral, an antiderivative of e to the x is just e to the x. And indeed, you're right, Curtis. I know you were thinking about this. I could factor that if I wanted to, but I'm not going to. I'm just going to plug in my bounds. So don't let me make a mistake on this one. Lots of ones and zeros floating around. 1 e to the 1 minus e to the 1. So those are just going to cancel. That's just 0. Plugging in the lower bound, 0 e to the 0, that's 0. So the only thing I've got left here is an e to the 0 or 1. There are 2 minus signs here. So it's just going to be 1 times 2 for a plain old 2, and that's pretty cool. That's a neat problem. I like that. You might think about this if you have especially if you have a CAS machine. You might think about graphing this expression. And you might go to the graph screen and take a look at this area from 0 to 1. And to me, it's just amazing that the exact area underneath that curve from 0 to 1 is 2. There's a transcendental function e. I've got this crazy square root function in there. And yet the exact area under there is 2. That's amazing.
Steve, that was something I was thinking about while you were, when you got this started, was looking at that and wanting to look at the graph of this expression. Wow. Okay.
And
that's really cool.
We'll leave that to Tom. He may have a moment to do that one, but I know he's got an idea, I think, on number 3. So let me take a look at that one, and then I'll turn it over to him. Okay. So this is a little bit different sort of a problem that involves integration by substitution, and one that you might not see right away. This is, I think, a classic sort of a problem for the AP calculus exam. We're given an expression here, 0 to 9, integral 0 to 9 of f of x is equal to 6, and we want to find that definite integral. See if we can get a number for that, an expression for that. Well, here's what I thought of immediately when I saw this. See if you're with me on this one, Curtis. When I saw the x times f of x squared, I sort of thought of what we did a moment ago. Maybe we need to use integration by parts here. But when I think about this a little bit further, I see an inner function here, and I see its derivative plus or minus a constant as part of that product. So I don't know where this is going to lead, but my vision, my calculus vision says, you know what? I'm going to try u equal to x squared and see what happens. So here's my original transformation. Du is pretty easy, 2x dx. And as usual, I'm going to solve for dx. It's du divided by 2x. This is a definite integral. And although it's got a function name in here, f, I still have to drag along the bounds. So when x is 0, u is equal to 0 squared or 0. When x is 3, u is 3 squared or 9. So here we go. Let's see what happens here. Here's the original expression. There's the x. This becomes f of u. And that's the expression for dx, and some good things happen here.
Hey, Steve.
Yes, sir.
I did get a question in the chat. Oh, never mind. Mark answered it.
Okay.
So it was a question about whether integration by parts was BC or AB. And it's only a BC topic.
Yep. Okay. So the x's cancel here. I've got a 1/2 out in front, and look what has magically happened here. I have this expression here. Remember that u is a dummy variable. And so that circled expression is just 6. And the answer to our problem, our definite integral, is just plain 3. That's kind of cool. All right, Tom, I'm going to give you a shot here to look at this one and maybe the graph, if you have a second. So I'll stop sharing.
Okay,
There you go.
okay. Let me find my screen here.
Okay.
All right, let me maybe clear that off here. Okay. Actually, it's as much as anything kind of a test taking strategy one might use.
Okay.
I could imagine that very easily being on the multiple choice part of the test, Steve, where they're
Absolutely.
and so since that has to be true for any function, continuous function f, it occurred to me that what we could do is bring up the math menu. And let's see, it was the integral from 0 to 9.
Yes.
And the function, when you integrated it, you got 6, I think, right?
That's correct.
Well, if this is going to work for any function, I'm just going to pick the easiest function I can think of.
Okay.
So let's see, if my interval's length 9, from 0 to 9,
Yes.
2/3 of that would be 6. So I'm
Okay.
just going to integrate the constant 2/3.
Okay. Which would be the function f, correct?
Yeah, that's my function. It's just f of x equals 2/3, no matter what x is.
Okay, gotcha.
It's just a flat line. And just verify, okay, we got 6.
Okay.
Looks good.
Okay.
And now I'm supposed to evaluate the integral from 0 to 3.
Correct.
Oops. X times my function. Okay, so that'll
Correct.
be x.
Well, it's the function evaluated at x squared.
But since my function's constant,
It's just
still
that
2/3.
constant.
It's
Yep.
still 2/3. So just put in a 2/3 here
Okay.
and see what we get.
Son of a gun.
There it is. All
Pretty
right.
cool.
So So there are questions like that where if it's supposed to hold in general and you can think of a function that will make life easy for you, go ahead and apply it. Now, I will be really quick to point out, though, that Steve, the work you did was actually showing why it works. And so, if there was a question that where one really needed to verify or explain what was going on here, that'd be a different story. But
Gotcha.
just
Gotcha.
kind of a cute thing we could do here. All right. Okay, I will.
Can you
stop.
look at that real quick, that e to the square root of x? Any chance of that?
E to the square root of x.
Yeah, that was part D.
Okay.
in the
Yeah,
graph.
sure. Okay.
Or while you're on the calculator screen, if you just did that definite integral, just curious if that comes out to be exactly 2.
Good question. Okay, let's try it real fast here. So we'll pull up our definite integral, and it was the integral from 0 to 1, I believe.
Yes, correct.
And that is curious that just e to the square root of x.
Correct.
Oops, went a little too far. There we go.
There you go. Beautiful. Let's see what happens.
Drum roll, please. Will we get to?
Oh, how about
very
that?
close.
How about that?
Of course, the numerical methods it's using there. So,
Sure, that's pretty cool.
all right. Great.
So Tom, before you leave that, we talk about this, you and I talk about this frequently, but if we did that on the graph screen, do we believe, and maybe Curtis has to answer this, is the numerical algorithm the same in the background so that it would produce, the same answer?
I don't know. Let's find out.
Yeah, go ahead and do it. All
I have
right.
my suspicions that that floating point arithmetic is going to be going to work out to be the same, but
Be the same, Curtis? Yeah.
that's anytime you're working in a computer of any type, you're going to end up with some kind of approximation that's going to happen here, and I suspect that it's using the same.
Okay.
Okay. So we want to calculate from
You want to integrate from second calculate and do the integration from 0 to 1 underneath of that.
number 7 there.
Yeah.
Lower limit, we're already at 0, right?
Yeah, x equals 0.
Enter that, and then we'll.
Upper limit, you can just type in the number 1.
Okay. Let's see, just type in 1.
Yeah.
Ooh,
That's
Slightly different. Okay.
slightly different, isn't it?
Yeah. So do you think does it depend on the graph screen? Does it depend on what sort of window you're in? For example, a front
Plausible.
window? Yeah, possible. Okay.
Possible. Mhm.
Okay.
Yeah.
Cool.
All
Okay.
right. Okay.
Thank you, Tom. Thanks, Tom.
Sure. Yeah, I'll stop the share and give it back to you.
All right, we've got one more good one, I think, tonight, Curtis, and we're going to leave people with a challenge problem for the Super Bowl tickets. Here we go.
Those Super Bowl tickets are on your couch. That's the seat.
That's where I'll be.
Just wanted to make sure we
All
all
right.
understand that that's where those are.
All right. But let's suppose that f is a continuous function on the interval 0 to pi. We want to show that 0 to pi x, f of sine of x, so that's sort of a composition of functions, where f is sort of this unknown general function, is equal to pi over 2 times the integral from 0 to pi f of the sine of x dx. Holy Toledo, that's a mouthful. So there's lots of little things going on in this problem. See if you can help me with some of this. Believe it or not, this is, I think that we solved this one by using an integration by substitution. So what I'm going to do, and it's not obvious here, it's not clear. If you thought about this one, if you looked at these problems ahead of time and thought about this one, it's definitely not clear what the substitution should be. It takes a little bit of trial and error, a good guess or two, thinking about some trigonometric identities to come up with what I think is the right one here, or a good one. So I'm going to let u be equal to pi minus x. How did I come up with that? Well, it took me a while here to think about this and to figure this one out. What's the derivative of that? Well, it's just a minus dx. I'm a little concerned. I have an extra x there. I've got a sign hanging around. I'm not sure exactly what's going to happen here, but I'm going to follow through my procedure that I've talked about this evening. So I'm going to solve for dx, and that's very easy. It's just minus du. Remember, I'm starting on the left-hand side, and I'd like to somehow end up with that expression on the right. So when x is 0, let's see, I get u is equal to pi minus 0 or pi. When x is pi, I get 0. All right, let's see what happens here. Curtis, don't let me make a mistake on this one. Here's the original expression. Well, let's see here. I'm trying to bring everything from the x world into the u world. So with this original expression, I'm going to bring it way over here. As we've done a couple of times this evening, I can actually solve that for x. So that x would be equal to, well, let's see, pi minus u. Why is that a good thing? Well, remember, I'm trying to bring everything from x's into the u world. So there's my pi minus u. I've got f of the sine of pi minus u, and boy, initially that looks like I've made things more complicated. But let's see what happens here. Now, in this next step, to go from here to here, I've done a couple of things. I apologize for this, Curtis. I haven't asked many questions out there, but here are a couple. Well, here's one anyway. This minus sign right here I got rid of because what I did was I switched the bounds. I used that property of definite integrals. But this f of the sine of this expression, I just wrote as f of the sine of u. And the question is, how come? How can you do that? Why can you do that? What did I do to get to that sine of u? Any ideas about that one? Any possibilities? What happened there? Well, we'll leave that open in the chat. Okay, Curtis?
I think that's a good idea.
Okay, here we go. So now what I did was I wrote this as two separate definite integrals. So I sort of distributed. I've got a pi times that f of sine of u. I've got a minus u times f of sine u du. Now, remember that those variables on the inside are just dummy variables. I brought everything into the u world. I'm not bringing it back to x's, but I'm going to write it with a different dummy variable, x. And now some really good things happen here. Because notice that this definite integral is exactly the one that I started out with. So the way that I think about this is that's an unknown variable that I want to solve for. I often call this my integral I. And so I want to solve for I. So I add I to both sides of that equation. I get 2 times my original integral is equal to this leftover definite integral. And I'm just about got it. I divide both sides by 2. And there's the right-hand side of that original expression. That's a nice problem. So that's kind of a dirty word. That's kind of a proof. We don't really see many of those on the AP Calculus exam, but that's a nice problem for some of your good students. That's a good problem for 8 o'clock tomorrow morning. And if they get that problem, here's the challenge question. See if they can use that result to somehow find that answer, that definite integral. I'm not quite sure how that applies here yet, but the hint is, yeah, somehow we can use this result in this problem up above in order to solve that. Cool. Curtis, any more lingering questions out there? That's all I got.
I don't think there's any lingering questions. Wanda did help you out there with the sign of a difference identity.
Very good. Excellent.
giving that out there.
Yeah.
She also is talking a little bit about the, if you look at the unit circle,
Yes,
you can kind of see that same thing happen. So
that's correct.
That's actually really nice. That's where my head kind of went, was the unit circle, trying to imagine that.
That's very good.
That
Exactly.
piece. So that's a good good strategy.
Yep, agreed.
Mark says he starts at 8:50 in the morning, so
All right, well, he can do that at 8:50 then.
he's
If he
gonna
wants
have
me
to
to,
do
if he wants me to zoom into his class, let me know, okay?
it. Don't offer that, Steve. You may end up having to do that.
Very
Well,
good.
I
Thank you.
really appreciate it, Steve. Tom, you have any other technology things? Otherwise, I'll wrap us up.
I think we're good.
Okay.
Very good.
Cool. So I will just make mention again, if you have had a chance as a teacher and you're watching this through tonight, you can email me. I'll put my email in the chat. It's the same as it always has been, curtis@ti.com. And I'll have that out there. You can email me and I will send you a link to a place where you can get a professional development certificate in 1 hour of that. And just wanted to let you know, in 2 weeks, we will have another one of these sessions. Hopefully my throat won't be quite as scratchy and hopefully my head won't be quite so cloudy tonight. So this was a great session tonight. Stephen, thank you,
Curtis.
for that. Tom, thanks for your input tonight. And yeah, this was great. So we'll see you guys in 2 weeks. I'll get the problems posted as soon as I can. And Steve, we'll get the solutions for tonight up in the next couple days.
Yes, and I would like to encourage people to send questions like we had one tonight. I think that was really cool.
Yeah, it was great. Send questions in also. You can use my chat, my email for that. So please send questions over. I know we got one from Michelle earlier tonight. And so certainly we'll take them. All right. We'll see you guys in 2 weeks. Thanks.
Thanks, Kurt.
Good night.